We're going to go through a first derivative test example here. So this is the setup for the example. Suppose that g of x is a function whose first derivative is this right here. So they actually don't tell us what g of x is. We have no formula or equation for g of x itself, but we do have a lot of information about the first derivative. And the first derivative test is a test which finds extreme values, maximums, minimums of a function. And this is a huge question in calculus, a huge question in mathematics, finding the largest, the smallest, the cheapest, the most expensive things. These extreme values are really important points in so many contexts, and so we spend a lot of time trying to find them. And this is one of the first tests that we come across, the first derivative test for finding an extreme value. So our first question is, our first task is they ask us to determine with justification, I love that, all critical numbers of g. So a critical number we're remembering is where the derivative equals 0 or the derivative is undefined. So a critical number is where g prime of x is equal to 0. We can think about what that means. If g prime of x is 0, it's usually topping out or bottoming out, or where the derivative is undefined. Okay, so let's first take the task of finding where g prime of x equals 0. So we look at this, we have g prime of x, and we have to think where could this equal 0? For what x values could this equal 0? Definitely, so it's a rational function. Definitely, we want to look at where the numerator could be 0, and we want to make sure and take special care of places where the denominator might be 0, because that could actually cause some problems. But this whole thing will equal 0 if this numerator is 0 and the denominator is behaving well. Okay, so where is x plus 4 or x minus times x minus 2 equal to 0? Of course, that happens at x equals negative 4 and x equals 2. Now, looking at this denominator, it actually behaves really well. For any x value and any real number x, this will be a positive number. And so this creates no problems. If this was a denominator that created 0 somewhere, we would have to kind of look more finely at that and make sure that these were still critical numbers. But everything checks out here. So these are our critical numbers for where g prime of x equals 0. And g prime of x being not defined, this derivative function here actually is defined everywhere. The only place it could have had a problem is if the denominator was 0, and that doesn't happen. So this is defined everywhere, so the only critical numbers will come from this possibility here. We're also remembering that critical numbers are the candidates for where a max or min of the function, one of these extreme values, might be occurring. So critical numbers are sort of like all of the suspects, and then we're going to look closely at them to see what's going on. And for that, we use what's called the first derivative test. Okay, our next question, which is sort of the meat of the whole problem, says by developing a carefully labeled first derivative sign chart, decide whether g has a local max, a local min, or neither at each critical number. So we got to test both these guys. We're going to create a carefully labeled first derivative sign chart, and we'll put our critical numbers on here, negative 4 and 2. And we're going to analyze the sign of that first derivative. So we basically have 3 regions on this number line delineated by these critical numbers. We've got all of these numbers here, we've got numbers in here, and we've got numbers over here. If we were to test a number right here and we find out it's positive, maybe, I don't know what it is, but we find out that it's positive, then it turns out that every number in this region will have a first derivative. The first derivative evaluated at these points will be positive. They have to follow. I'm just realizing that we're not talking about f, we're talking about g, so sign of g prime. Same story here. If we find out that these are all negative, or that one point in here is negative, then all of these will have, if you evaluate the first derivative at any of these points, it would have to be negative as well. So these are like little clusters as far as the sign of the first derivative. Within a region, they all behave the same. And this is because if you think about it, these critical numbers, these are the places where the first derivative is 0. These are the places where that first derivative function crosses the x-axis from negative to positive or possibly positive to negative. These are the only numbers we found. So they're the only places where the function is like crossing that border between negative and positive or positive and negative. And so you can't have numbers that are positive and negative first derivative within a region, because it would have meant that somewhere along the line you had a 0 derivative, and that only happens here and here. Okay, so let's test a number. We'll pick a number right here, like maybe -10, and we'll see back up here what the derivative, if it's positive or negative. We can do this pretty quickly, but I'll write it out this first time. -10 minus 2 over -10 squared plus 1. So this is going to be negative times another negative, that's positive, over, this will be a positive number. So we have negative times a negative over a positive, that's definitely a positive number. So this whole region here, after our test point, we find out that the first derivative will be positive in here. Okay, we'll take another point in here. We could test like 0, and we can pretty quickly decide whether the first derivative is positive or negative. 0 plus 4 is positive. Then 0 minus 2 is negative. Over 0 squared plus 1 will be positive. So all of these values in here must be negative for the first derivative. Okay, and then we can test another point, like maybe 10, and do that one also pretty quickly. 10 plus 4 is positive, 10 minus 2 is positive, and the denominator is always positive. So all of these values are positive. So we know exactly how the sign of g prime is behaving for any real number. So what does that tell us about the behavior of the original function g, which we were never given? We don't know. All we know is the first derivative, but we know that g is increasing at this point in this region. That's because the first derivative is positive. So all of these numbers, g is growing, growing, growing. And then for the other this region in the middle, g is decreasing, and then it's increasing again. So I think you can already pretty much tell that this at -4 we have a maximum, at 2 we have a minimum, because it was decreasing and then it starts increasing at 0. The first derivative is 0 at both of these places. We don't know exactly, it could be very dramatic, but we do know increasing, decreasing, and where the first derivative is 0. So this at -4 we have a local max at x equals -4, and we're going to have a local min for the reasons we just talked about at x equals 2. Let's just be sure we answered their question. We first drew a sign chart, local max, min, or neither at each of the critical numbers, and we did that. Okay, the next question is, does g have a global maximum, a global minimum, and justify your claim? So global maximum would mean that it is the highest point of the whole function. The function never gets higher than that. So this right here, if we had this right here would be a local maximum, but not a global maximum, because later on the function gets higher and higher. So the question is, does g have a global maximum? Well, let's go back to our sign chart and remember what this function must look like. We are increasing, increasing. When we get to x equals 4, we start decreasing, decreasing, and then when we get to x equals 2, we start increasing again. Importantly, this end behavior here, this is forever decreasing. It keeps going down, 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 because it never turns around. There are no other critical numbers, so it has to keep, I'm sorry, not decreasing, but it is coming from, the end behavior is that it's going down to negative infinity. Over here, the function is increasing, increasing, and going up to positive infinity. So we see that this and this are actually just local max and mins. There's no way that this could be a global and this can't be a global because of the behavior. If we had had a function kind of like this, where we maybe only had one critical number and we knew that it was always increasing on the left and decreasing on the right, we could say that for sure it would have a global max at that point. But we don't have that case. We have something that looks like this, so we have no global extrema. So a way we could answer this question is by saying there is no global extrema, only a local max and a local min. And this is because, as we're trying to justify it, as x is going to negative infinity, so as we're going out this way on the number line, the function is going to negative infinity. We know that it is heading this way because of the sign chart. As x is going to positive infinity, so for all these x values forever after, the function is going off to infinity. It keeps increasing, and so there's no way that these guys can be global max and mins. The last question or last job that we're asked to do is sketch a possible graph of g of x. Clearly label any local or global extrema on the graph. Okay, we don't have a lot of information. There's no way we can know what the output values of g of x are. We only have, this information for the derivative, and we do know where a local max and min are. So let's just do our best here. So here we have, let's see, we'll draw it this way. We know that at -4 and 2, important things happen. So as we're approaching -4, the function is increasing, increasing. Right at -4, it tops out. It has a local max. And then as we approach x equals 2, it's going to bottom out, and then it's going to forever be increasing. So local max. At 4, we could say g of 4. We don't know what this point is. And a local min at 2, g of 2. That's about as good as we could do. We don't know specific y values for this function, but this gives us a pretty clear idea of the shape of this function.